for example, here use the variable. Use the variable which describes the state of a physical system. It is assumed sufficiently smooth. So when I write this equation in this form, it is understood that dy u dy x and dy u dy t, they are of class C1, right? When I write like this is sort of a model. When I write like this, ux and ut, they are of class C1, and I will take that these functions, coefficient functions a, b, c, here I will assume that they are also of class C1. Is it all right? Hello?
Yes, sir.
Wherever there is a doubt, please don't hesitate, and because this is the purpose of this workshop, things should be very clear. If there is any doubt, don't hesitate. Please do ask. So up till now, is it okay? Any question?
No, sir.
All right, very good. So now, for such equations, look here, there is a method called method of characteristics, right? Now, but normally, what do we see? That suppose if this is, had it been say y, for example, in geometrical problems, you see normally this is x, y, right? Instead of t, it is y. Instead of t, it is y. So this is x, y, u space. Here t plays the role of y. I have just replaced t by y here. All right. So you see, I can write this as the dot product of two vectors. Is that right? Because a, b, c, this is one vector. Because the solution of this, let me write this as equation number 1. Solution of 1 will be of the form, naturally, u as a function of x and t, right? We expect that this is the graph of the solution surface. Take this t as y, so it is an x, y, u space. So in x, y, u space, in fact, it is the graph of a surface. Is that right? U is right. U as a function of x, t, y, or you can write x, y. Is that okay? So solution we expect to be of the form u as a function of x and t. So here I will write y and t, right? I mean y is replaced by t or t by y. If I'm talking about the geometry, I will take y into consideration. But if it is a physical situation, I will replace y by t. All right. So what do we find? We find that solution has to be of this form, right? And if the solution surface is like this, I can write this function phi. I can write this function phi as say u of xy minus u. I could have taken u as psi, some function, right, instead of u, but it is a very standard notation. Instead of writing u as a function as psi of xy, I think it is all right. It is understood that this is some function of x and y, and I have denoted by u. All right. So this is the function, right? Capital phi. Now look here. This represents a surface. F is equal to 0. This represents a surface. What are the gradients? We know that gradient of this are nothing but phi x, phi y, and phi u in the x by u space. Is that right? And what is phi x in this case? It is ux. What is phi y? It is uy. And what is phi u? It is minus 1. And what does it indicate? The gradient of a scalar field? Phi is a scalar field, right? Because this is a map from R2 to R, so
normal to the surface.
This is normal to the surface. Is that right? This is normal to the surface, phi equal to 0. So this is all right. So if you just look at this partial differential equation, I can write this in the form. This function a, b, and c. So Actually, this is a vector field, right? It is a vector field in XYU space or XTU space, same thing, right? This dot UX, UY or UT, right? -1, this is equal to 0. Here it is T, so I will take T, it's all right. So it's right. Y, as I said, that Y and T, I mean, they indicate the, same stuff. So the dot product of these two vectors, this differential equation can be written in this form, the dot product. So this is a vector field. So the differential equation may be regarded as representing a vector field in this space, XTU or XYU space. This is right. So differential equation, in fact, can be represented. So this is the direction field. And what do we get now? It is very clear that if you think of this, I mean, the solution is going to be the integral surface of the vector field. Because what happens, it's very clear from here that if you think of a point in XYU space, starting from some given point, say X0, Y0, U0, if this particle moves in space in such a way so that the tangent at each point coincides with the direction of this vector field, then what will happen? A space curve would be generated. Is that right? It's very clear that this is normal to the surface and this is perpendicular to this because the dot product of these two vectors is 0, and therefore this vector field lies in the tangent plane to the surface at that point. Is that right? Hello?
Yes, sir.
Yes, sir.
Yeah, very good. So it's very clear, as I just said, that if you think of a particle moving in space in such a way so that tangent at each point is in the direction of this vector field, what does it mean? This means that dx ds is A, dy ds is B, and du ds is C. This is the meaning. A particle is, so this is the curve which is generated, that is x. This is the parametric representation of that curve. Y or t, it's one and the same thing. U as a function of s. This is some curve, is that right? As this point, or you call it a particle located at this point, if it moves in surface, in a space, in this space in such a way so that tangent to the path at each point coincides with the direction field at that point, then a curve would be generated, and this curve is given by the solution of these equations. Is that right? Hello?
Yes, sir. Yes, sir.
So this is called, these are called the characteristic curves. These are called the characteristic curves of the differential equation. These are called. So it's very clear that these characteristic curves, as a matter of fact, they lie because at each point, the tangent is in the direction of this, and this vector lies in the tangent plane to the, is that right? So we can see that solutions, in fact, the locus of all such curves, these are called the characteristic curves of the differential equation. All these curves, they lie on the solution surface, and the locus, in fact, that will give you the solution surface itself. So in fact, the characteristic curve, you can see it is the integral curve of this vector field. Is that right? Dx ds is A, dy by ds is B, du ds is C. So the characteristic curve is an integral curve of this vector field. And what is integral surface? Because the solution of this, now yes, before that I will talk about the Cauchy problem now. So up to here, is it all right? Hello?
Yes, sir.
All right. So let me talk about the Cauchy problem. What is Cauchy problem? Cauchy problem asks for determining the solution of this differential equation, right? Satisfying some initial condition, and that is the values they lie on the. So let me geometrically. So I will take t as y. So it's clear. X, y, u space. This is the curve specified, right? I will call it gamma naught. This is the curve specified, and at every point of it, u is specified. This function, known function, is specified. So these are the coordinates x, y, and at each point of this, u is specified. U is equal to u naught of x comma y. I mean, this is specified. So if I take this curve gamma naught, if suppose gamma naught is parametrized, if gamma naught is parametrized, is it visible? If it is not visible, please, because my focus here is on the paper. If it is not visible, please remind me. So, all right. So if gamma naught, so this is your characteristic. I will call it the characteristic curve. Parametric equation of the characteristic curve. Now gamma naught, this is the base curve, right? Is that okay? It is in the plane xy plane. So I can always characterize it. That is x as some function of xi, y as some function of xi, and then u is specified. So u is equal to u naught of xi, yxi, that eventually it is some function of xi. Right? So this is the curve specified in the plane. What is Cauchy problem? Cauchy problem, in fact, asks to determine a function u which satisfies the differential equation identically and takes on some specified values on this curve, gamma naught. This is your Cauchy problem. So actually what we do, we take the corresponding space curve, and this is your, this is the curve gamma naught. I mean this gamma naught is the projection of this in the xy plane. Is that okay? And this point, so this is your x, y, and then u. What is u? U is equal to u of xy. Because at each point u is specified, so the situation is somewhat like this. Problem is to find the characteristic curves, because now you look here, which span the solution surface. Now, so from each point of this, so you see the Cauchy problem is best. I mean, to solve it, the best procedure is to flow out from each point of this given curve, right? Flow from each point of the given curve in the direction of the characteristic curve. Is that right? So at this point, in fact, if suppose, so these are the characteristic curves, means S is the parameter along this characteristic curve, and let's take xi is the parameter along this given curve. So if we are able to find these characteristic curves, then the union of all these characteristic curves, I mean, it will be nothing but the required integral surface of this vector field A, B, C. That is the whole idea. Is it all right, please? Okay. Hello?
Okay, sir.
So sorry to disturb.
Sure. No, it's very good. I think you should ask some question. Yes.
We are looking for that solution u which satisfies this condition that on this xy plane it must have this prescribed value of u naught.
Yes.
Right?
Yes.
And then you take the projection of this, and this last step is not clear to me. Can you just explain?
No, this is specified. This is all right now. So
yeah,
this is
all right.
So this is known to me. Height is known now. You know.
Yes.
At each point.
Yes.
At each point, height is known. So I can think of this space curve gamma. Is that right?
Right.
At each point, I know what is u. So just so that this becomes the projection of this space curve here in the xy.
At that height. Okay.
Is that right?
Right.
Okay.
And through that gamma, you are trying to find out the characteristic curves from this point which have the same direction, ratios coincides with dx by ds is equals to a and dy ds is equals to b and something like that.
In fact, these are the characteristic curves, which what I have written here, dx, ds is a, dy by ds is b, du,
Yes,
ds is
yes,
c.
yes, yes.
So you see, in xy, in fact, they are the projections here. This is the base characteristics, as a matter of fact.
Actually, initially the book we got confused in gamma and gamma naught.
Oh no, absolutely, there is no confusion. There is this. These are equivalent. You see,
Yeah, they are equivalent in
in the sense that I specify you at each point of this.
yes sir, yes sir.
And this is equivalent to asking, what is the Cauchy problem? Cauchy problem asks for determining a function u, right? Which satisfies, it takes on the prescribed values on this gamma naught. So in the neighborhood of this, I look for the solution in the neighborhood of this such that it takes on specified values on gamma naught. Is that right? Hello?
Yes sir, yes sir.
So this is equivalent to asking, you take this space curve. Is that right? This
Yes,
problem
yes,
is equivalent to this problem. That is, we are looking for the solution which satisfies in the neighborhood of this gamma, which takes on the specified values here. So what are the specified values? X, Y, u of xy, which is this.
yes, yes, yes,
So
sir.
both these problems are equivalent.
Yes. Now, yeah. Now
Is it all right now?
now it's clear, sir. Yes.
Okay, very good. So, so this is Cauchy problem, which is extremely important. It asks for determining a function which satisfies the differential equation identically, and it takes on specified values along this curve. It means passing. We are looking for a surface which contains this space curve precisely. Now the problem is this. Is that right?
Yes, sir. Yes, sir.
Solution is a surface which contains this space curve gamma. All right. So, so look here at now. So what I said just now, the best way to solve this Cauchy problem is to move away, right? Is to move away from the given curve. This is your given space curve. Take any point here. This s is the distance measured, or this is the parameter along this curve. Xi is the parameter along this curve, right? And so you just move away from it. That is, all these characteristic curves, they emanate from this. Is that right? So at this point, s is equal to 0. Is that right? S is measured from this point.
Yes, sir. Yes, sir.
And psi is the parameter along this curve. So at any point in this region, the entity would be a function of s and psi. Is that right?
Yes, sir.
So, in precisely what we are doing, this is a system of first order ODEs, and at s is equal to 0, we know these conditions that x is equal to x of psi, y is equal to y of psi, and u is equal to u naught of psi. Like this. Is it all right? Hello?
Yes, sir.
So, yes. So the union of all these characteristic curves, in fact, that will generate this. How we will see that whether it happens, how does it happen? It's very clear that now, so this is a system of first order ODEs. A, B, C, they are very nice functions. In the beginning, I assumed that they are of class C1, and therefore there exists a unique solution for this system of ODEs. Is that right? Hello?
Yes, sir. Yes, sir.
Yes, sir.
Yes.
Yes. Since these functions, they are differentiable, class C1, so definitely there exists a unique solution of this system of ODEs.
Yes.
Okay.
Each that means each curve from that gamma
Yes.
must
Very
satisfy this ODE system of differential equation.
Very right. A union of all these characteristic curves. So actually, let us see what happens when I solve these equations. When I solve these equations with this initial condition, that at s is equal to 0, x is equal to x of psi. So finally, I am going to get x as a function of psi and s, y as a function of psi and s,
Right.
u as a function of psi and s. Is that right? Hello?
Yes, sir. Definitely.
this system of ODEs, together here S is a parameter, right, which belongs to some interval which is contained in R. Is that right? Here also xi is some parameter which belongs to some interval contained in R. Okay, and at S is equal to 0, these values are specified, so we can solve. Definitely a solution exists and it is unique solution of this system. Now the question is this: what do they represent? X as a function of S and xi, Y as a function of S and xi, U as a function of S and xi. Geometrically, what does it mean?
That means this is a parametric surface. We are looking for.
Very good. These equations, they do represent, because what happens? Not always. You see, it is a surface only if the first two equations, if I am able to solve xi as a function of x and y, s as a function of s and y, and I substitute here in the last, then it is a surface. Otherwise, not.
Yes, sir.
And moreover, uniquely, that s from the first two equations. So let me write. This is the equation that is under consideration. That is a of xy ux. I'm sorry. A, which is a function of x, y, and ux, plus b, which is a function of x, y, uy, and this is equal to c, which is a function of x, y, and u. So we have arrived this set of equations, that is the characteristic curves for this differential equation are given by these equations. That dx ds is a, which is a function of x, y, and u. Similarly, dy by ds is a function, it is x, y, u, and du ds is c, which is a function of x, y, u, right? S is a parameter, so it's all right. Now, here, satisfying these initial conditions, that at s is equal to 0, we have x is equal to x of xi, y is equal to y of xi, and u is equal to u naught of xi. Is that right? Some initial conditions were specified here, so we can always write that this is your, as a matter of fact, this is the given curve. This is the given.
That means you reduce original problem of Cauchy problem in this particular.
Yes.
Okay, yeah.
The problem of solving the problem. This is the initial condition. Say u is equal to u naught of x comma y. For example, if I write like this, u is equal to u naught of x comma y. This is u is equal to u. Is that okay? Say, for example, if I say that at y is equal to something, so that it turns out to be say y is equal to say y1. Is that right? Hello? Or y is equal to some function of x.
Yes, sir.
So, as a matter of fact, it has to be a curve, right? It has to be a curve which I say that gamma is the curve,
right,
which I have parameterized. Problem is to find a solution of this partial differential equation, right? Which is a surface containing this curve, space curve.
Right.
So, problem of solving a partial initial value problem involving a partial differential equation reduces to a problem of solving ODEs. Is that right?
Yes, sir. Yes.
Yes, and since A, B, C, they are of class C1, so definitely this initial value problem, which involves a system of ODEs, has a unique solution. All right. So what the solution is of the form I have just mentioned, that x is equal to x of xi s. Now still problem is not yet over. This is a function of xi and s, and u is a function of xi and s. Now, if I am able to solve these first two equations, That is, if I'm able to solve xi as a function of x and y and s as a function of x and y, then I can substitute these values here to get the solution. U is equal to u naught, psi is a function of x and y, s is a function of s and y, and so eventually this is a function of x and y. Is that right? Hello?
Yes, sir. Yes, sir.
But the thing is this, is it always possible to solve these two equations for psi and s uniquely?
That can be possible only when Jacobian is non-zero.
Very right. This is called inverse function theorem, right? Here is the idea of inverse function theorem. This is possible. This inversion is possible only if the Jacobian of the transformation from xy to xi s. Is that right?
Yes. Ultimately, I mean, solving this system of ODs with given some initial condition
Yes.
in that parametric surface,
Yes.
we need to find out the new variables, which we say xi and s say.
As I said, as I explained, the Cauchy problem, the best way to solve the Cauchy problem is to flow out from
Right.
this is given curve. Flow out and take characteristics emanating from each point. It is in the direction of this vector, right?
Right,
That is,
right.
ABC. That's right.
Right.
So these are the correct. This is the best way. This is the best way of solving, and this is precisely the way we solve this Cauchy problem.
Yes, definitely. This is the
So
very
this
well
is
analytical.
S is this and psi is this.
It's
These
this.
are the two parameters.
Right.
So now at this point, at this juncture, we should be able to solve psi as a function of x and y uniquely, s as a function of x and y uniquely. If this is possible, then definitely it is an integral, and we substitute here, we get the integral surface, right? But if it doesn't work here, then perhaps, yes, it's not a surface, it's not an integral surface at all. There is a problem. Is that right? If this condition is not satisfied, if this
Okay.
that is
That
very
means every time Cauchy problem is doesn't have solution. That doesn't. It's like
precisely, not always, not always.
okay.
We should be able to solve that these first two equations for s and xi. If we are able to solve these first two equations for xi and s in terms of x and y uniquely, then we get a unique solution of this. So in fact, it ensures uniqueness, right? It ensures uniqueness of the solution. And for that, what is the condition? First of all, xi, right, this Jacobian, the Jacobian of the transformation, this should be
Non-zero.
this should be different from zero. Jacobian of the transformation should be different from zero. That is your xi, this is your xs, this is your yxi, this is your ys. I mean, this should be different from zero. This is, you see here, si is any point. Now, because of the continuity, all these functions, in fact, I have taken to be of class C1. So the continuity ensures that if it is non-zero here, it will be non-zero here also. Is that right? Because of these functions, they are continuous. Xi, right? Xi.
Right, sir.
So because of so even if you take S is equal to xi, I mean, this is the condition which ensures that the solution exists and it is unique. So this is to be seen every time. This is to be seen every time to find out whether the solution exists or not. All right. So with this, now I come to a very important this physical equation with which perhaps you are all familiar. Let me write this. Just 1 minute. Yeah, very right. So this is your ut plus c naught ux equal to 0. Right? You think this is the simplest equation one can think of. Is that right? This is the simplest considered. But this is linear. This is linear, and I mean, is that right? And I'm sure that it is taught at the undergraduate level in most of the universities, where in third year they have this partial differential equation course. It is taught at the BSc level. Am I
Yes,
right?
yes,
Am I
sir.
right?
Yes, sir.
Yes. So what are the characteristics? If you write the characteristics following this, what we have done just now, the characteristics are dx, ds. This is your C naught. Am I right? dt, ds. This is your 1. Okay, here coefficient is 1. Here coefficient is C naught. And du, ds is your 0. These are the characteristics of this partial differential equation. Is it all right? Hello?
Yes, sir. Yes, sir.
And suppose this is the initial condition that u is equal to, at t equal to 0, for example, let us say u is equal to u naught of x. This is the initial condition specified. So I can write this. This is a curve, right? This is a curve in x t u space. So I can parameterize this curve. That is, this curve I will denote it by gamma, space curve. Space means for x t u space. So what is this? X is your xi. So x is your xi. X is a function of xi. Is that right? X is a function of xi, which is nothing but xi.
Yes,
What
sir.
is t? T equal to 0, and u is equal to u naught of xi.
Xi.
So
Right.
these are the parametric equations, correct?
Of this curve on xt plane.
This is a space curve, no, not plane. This is a space
Sorry,
curve.
space curve.
X T U space.
Okay, fine.
So
The curve one, right.
the position vector depends on one parameter, right? The position vector of a point in space depends on one parameter. The locus would be a curve in space. Is that right? Here the position vector depends on two parameters, and therefore the locus of such a point in R3 would be a surface. Is that right? Provided, again, the same thing, I repeat, that we should be able to solve these equations for xi and s uniquely in terms of x and y. And if you substitute this here, then only you get that surface. Is it all right? Hello?
Yes,
sir.
All right. So these are the characteristic curves, and this is the, which of course are the conditions at s is equal to 0, which I mentioned here. Right? The best way to solve is to flow out from this given curve in the direction, right? In the direction of the this vector field ABC. This is precisely the characteristics. The characteristics emanating from the, right? They originate from points on gamma. Is it all right? Hello?
yes,
So,
sir.
so these conditions are specified at s is equal to 0. So we have got a system of ODEs satisfying these initial conditions. So quickly I can solve. From here I get x is equal to c naught s plus an arbitrary constant. Arbitrary constant can be obtained using these initial conditions. But at s is equal to 0, x is equal to xi, so the constant is xi. Is it all right? Hello?
Can you explain this step again, sir? How you start?
Yes. Look here. This is the first equation, right? Now I have to solve these equations.
Okay.
Equations subject to these conditions. So I'm integrating this first equation. Here it will be some constant. Is that right?
Right. Then we can just have this initial condition and
X is equal to c naught s plus constant. Now, in order to determine this constant, make use of initial condition, that is that s is equal to 0, x is equal to xi. So the value of the constant is xi.
right, sir, right.
So I will write x is equal to c naught s plus xi. You can see here at s is equal to 0, x is equal to xi. This condition is met. Is that all right? Hello?
Yes, sir. Yes.
Very good. Similarly, the second equation will give me what? T is equal to s plus some constant.
And and s is 0, t is 0, then this is t is equals to
Yes.
say
S itself.
S
That's
is right.
This constant turns out to be 0 because at s is equal to 0, t is 0. So constant is 0. So the characteristic is t is equal. This curve is that right? T is equal to s. The third one, u is equal to, what do we get? U is equal to
equals to z
some constant.
constant.
And now how to determine this constant? because they are functions
Constant
at s is equal to 0, u is equal to u naught of xi, and therefore constant should be u naught of xi. Is that right? So
U
u
is
is
equal
equal
to U
to
naught
u
of
naught of xi. Is that right?
right, sir.
Now, from here, as I said, from the first two equations, we should be able to solve S and Xi uniquely. And this is possible here because the Jacobian of the transformation, you can quickly see that. So, what do we get from here? You can see here Xi is 1.
Right. S is equals to T and
So, from here we get
S is equals to T
yeah, S is equal to T. I will substitute
and
here
I is equals to
Xi is equal
naught
to
plus
x minus
minus
c
C
naught,
naught T. Right, right, right.
and of course s is equal to t. Is it all right? Hello?
Yes, sir.
And now in order to get this surface, I have to just substitute xi here, that's all. So u is equal to u naught of x minus c naught t. Is it all right? Hello?
Yes, sir. Definitely.
So this is the unique solution of this first order partial differential equation satisfying this initial condition. One can quickly verify that you see, this solution means what? It should satisfy the initial condition. It should satisfy the differential equation identically, right? Obviously, it satisfies the initial condition because at t is equal to 0, u is equal to u naught x, obviously.
Yes, sir.
It satisfies the initial condition. Now, what about the partial differential equation? You can see here.
Just differentiate it with respect to T and U.
So what it would be, the derivative with respect to t, what you are going to get?
It's U naught x minus C naught into minus C naught.
Yeah, so u prime.
You can say, yeah, sorry, so sorry.
This is called, what it is called? Hello?
Hello, sir. Yes, sir. Okay.
I'm using chain rule.
Yes, sir, definitely.
So u naught prime means derivative with respect to the argument function.
Right.
I just denote this as, say, some variable eta.
Right.
So u naught prime eta into derivative of eta with respect to t, which is the minus sign c naught.
Right.
And similarly, what is ux? Is simply u naught prime. Prime means derivative of u naught with respect to this argument function, which I said is eta.
Right. And adding of the...
Yes, multiply this equation by c naught and add, what do we get?
Substituting in main equation, you get equal to 0.
Yeah, very right. Multiplying this by c naught and adding to the first, we get this. So obviously, this is a unique solution of this initial value problem. Is that right? Hello?
Right, sir, right.
So now we have a very interesting result. We considered this simplest differential equation, that is deva u deva t plus c naught deva u deva x, this is equal to 0. Satisfying this condition at t equal to 0, u at t equal to 0 is u naught x. This is your initial value problem. And the solution is given by, it has a unique solution, which is your u is equal to u naught of x minus ct, c naught t. Is that right?
Yes, sir.
At t equal to 0, u is equal to u naught x. So you can see here in the x tip, let us see what happens in the ux plane. This is your ux plane. Okay? This is your ux plane. So at t equal to 0, u is equal to u naught x. Suppose the initial profile is somewhat like this. It is given to me. Initial profile may be e to the power minus x square. Is that right? Hello? So it will have this form. I mean, this your origin is slightly. I mean, this will be the origin. Is that right? Hello.
Okay, sir. Okay.
But I mean, this is a given function. So u is equal. Suppose, assuming that this is the initial profile.
Okay.
What does it indicate? This indicates that this initial profile is transmitted from one part of the medium to another part without any change in its shape and speed. Look here, at any time, this is at t equal to 0. This is at t equal to, I mean solution at any time t.
Yes, sir, it will translate, yeah.
Simply it will translate. That is, only x is replaced by c naught t. This distance is your c naught t. Each point, this distance is your c naught t. Each point on the profile, solution can be obtained from the initial profile just by displacing each point here a distance c naught t towards right. Is that right? Hello?
Yes, sir. Yes, sir.
That is, solution at any time t can be obtained from the initial profile by displacing each point to the right by a distance c naught t, right? By displacing each point to the right, a distance c naught t towards. Is that right? Hello?
Yes, sir. Yes, sir. Understand.
So, and interestingly, what is the speed of each point? ddt of x, that is c naught. So each point on the profile is moving with the constant speed. So I would say that the profile is moving from one part of the medium to another part without any change, no change in shape and speed. No change in shape and speed, right? Where does it happen? It happens, yes, in a wave propagation problem.
Yes, this is a wave propagation.
Oh, so it's very interesting. The solution of a first order PDE, the solution of a first order initial value problem, which involves a first order PDE, the solution represents a wave phenomenon, provided it is well posed, represents a wave phenomenon. What does it mean? A well posed Cauchy problem. This is nothing but a well posed Cauchy problem, right? Or I would say the solution. The solution of a well posed Cauchy problem represents a wave motion. It represents a wave. Is that right? Hello?
Yes, sir.
So a very important result, you say. I mean, the solution of a well-posed Cauchy problem represents a wave motion. These are called that's why they are called hyperbolic waves, right? A Cauchy problem, right? A Cauchy problem which is well-posed. The solution of such an initial value problem is referred to as a wave motion. It represents a wave. Is it clear to you? Hello?
Yes, sir.
And let me tell you, this is the simplest equation one can think of. It is taught at the undergraduate level. It's very, very elementary, but very interesting in the sense that it shows a connection between the wave motion and the solution of a Cauchy problem.
Yes, sir.
Yes. All right. So this is something which is very, very simple. And I tell you, this appears in a large number of physical processes. This simple looking equation. Because if I take Euler's equations of gas dynamics, okay? Have you heard of Euler's equations of gas dynamics? Or those who work in solid mechanics or fluid mechanics or plasma dynamics, perhaps they know what are Navier-Stokes equations, right? Navier-Stokes equations, they involve viscosity and thermal conduction. In the absence of viscosity and thermal conduction, the Navier-Stokes take the form of Euler's equation. Is that right?
Okay, sir. Okay.
And these Euler's equations, when you just consider one-dimensional system, it is a system of first-order PDEs. Right? In the asymptotic limit, in fact, that reduces to a single equation of this kind. Right? That reduces to a single equation of this kind. That's very interesting, but of course, instead of this scalar function, we get a vector function, but essentially the same result. Even you say, if suppose U represents the concentration of a fluid, right? If you of some pollutant, I would say pollutant. If U represents the concentration of a pollutant which is spilled in a stream which is moving from left to right with a constant speed C0, then it can be shown that the evolution of U at later time is governed by such an equation. Anyway, this is the application part. So what I want to say, this linear case is indeed trivial. This is a trivial case. However, its nonlinear counterpart. What will be the nonlinear counterpart? Deva u, deva t plus c, which is not constant, but it is a function of u. This function, unknown function. Deva u, deva x, this is equal to 0, and the initial condition that u at t equal to 0 is equal to u naught x. This is initial. So tell me, what is the nature of this partial differential equation?
This like as in the initial the above problem, it was C0, the fixed shape and fixed speed.
So as per our classification, what we will call it?
We will call it okay. C. This is the function of u. This can be linear. Just a second.
No, it's not linear.
Quasi-linear.
Semi.
Yes, yes. Somebody said quasi-linear, correct?
Quasi-linear, right?
Quasi-linear. See, if you remember,
U is there in quasi-linear. Yes.
If you just recall, in the first page, I said that if the coefficient functions, they depend on u.
U, yeah.
UUT. So this is quasi-linear. This is quasi-linear. This is quasi-linear. So let me number them. 1, 2. Okay. This is number 2. All right. So this is quasi-linear. So if it is a quasi-linear partial differential equation, look here. Here, this looks very trivial. This looks very simple. But I tell you, the study of this leads to most of the essential ideas associated with nonlinear hyperbolic or quasi-linear hyperbolic waves. In higher dimensions, once we understand the basic essentials with regard to this single equation, we understand what higher order equations, how do they behave, and everything would be known, you see. So this is quite deceptive. This looks very simple, but it's not that. It's quite involved. But it is not quasi-linear. So I will write it is quasi-linear. A great distinction between linear and quasi-linear. Can you tell me what are the characteristics of this equation? Dx
upon
C, right? So what are the characteristic curves? Now in short, I will write everything. There is no need of repeating everything which I have done. These are the characteristic curves. Dx dt is equal to C of u. Am I right? Hello?
Yes, sir. Yes, sir.
And along these characteristic curves, du ds, this is equal to 0. Or du dt, you can see, du dt equal to 0. Because deva u deva t plus deva u deva x into dx dt, this is nothing but the total derivative. Is that right? Hello?
Yes, sir. Yes, sir.
So along these characteristic curves, this happens. This happens means what? U remains constant. Along these characteristic curves, U remains constant. And if U remains constant, I can integrate it. Hello? Because U is constant, so its integration will give me what? T times C of U plus some constant, and that constant I can find out that is at t equal to 0, x is equal to z. Right? This is your space curve. I can parameterize it. That is x is equal to xi, t equal to 0, u is equal to u naught xi. Is that right? Hello?
Yes, sir. Yes, sir.
These are the characteristic curves, right? And they give one parameter family of characteristic curves. Along these curves, u remains constant. The total derivative is 0. So it means u is constant. If u is constant, means right hand side is constant. And if right hand side is constant, I can integrate it. Hello? Is it clear?
Yes, sir. Yes, sir.
Yes, very interesting. And u remains constant. So constant can be determined using this, that is u is equal to u naught psi. So this is the analytical form of the solution. You see, I have cut short. This is the method. This is the method which I have described, but there is no need of repeating it again. It's very clear that this is the analytical form of the solution. This is the analytical form of the solution. X is equal. What is xi? Xi is, this is the xt plane. This is your x. This is your t. At t equal to 0, at t equal to 0, x is equal to xi. So xi is any typical point here. Xi is any typical point here. So what happens here, that you see, if at t equal to 0, at t equal to 0, u is equal to u naught xi. So what is the value of u here? U is equal to u naught xi. What it says, that x remains constant. That is along this characteristic curve. This is the equation of this characteristic curve. X is equal to xi plus t c of u. That is along this characteristic curve. U is equal to u naught xi on the whole of it. Am I right? Hello?
Yes, sir. Yes, sir.
Because u remains constant. U remains constant along these characteristic curves. So whatever the information is available here at t equal to 0. Yes, any point, please? Hello? Pardon?
No, sir. No, sir.
Okay. So at t equal to 0, whatever the information is here, this information is propagated along this characteristic curve. So it is, this equation is x is equal to xi plus t times, is that right? Here u is equal to u naught xi. U is equal to u naught xi. On the whole of it. On the whole of it. So it means, and this is our objective. If we know the condition on the initial data, our objective is to find the solution in this domain. This is a typical characteristic of the family. I take all the characteristics, right, from minus infinity to plus infinity, and the union of all these characteristic curves, they generate the solution. Precisely this is the one. U is equal to u naught xi and x is equal to t c of u plus xi. Is it all right? Hello? This is the analytical form of the solution.
Yes, sir.
So in fact, along these characteristics, u is this, so I can write that this is the family, typical family of the characteristic curves, t, c of u naught xi. This is your u naught of xi. U is u naught xi. Let me call this as xi plus t times some function capital F of xi, where capital F of xi is nothing but c, which is a function of u naught of xi. And remember, u is nothing but your u naught in the whole reason. Whatever the information is, so characteristics, they are the wavelets, right? They are the wavelets, leading wavelets, along which, I mean, the information gets, is that right? Along which you get the same information which is available here at t equal to 0. They are the moving wavelets, and the behavior of the solution along these characteristics, that u remains constant. Is it all right? Hello?
Yes, sir. It's just one thing which, as you said initially, that चाहे हम स्पेस कर्व के थ्रू चले गामा पर और या फिर गामा नॉट जो हमारा
अब हम स्पेस कर्व की ही बात कर रहे हैं, वो तो now this is the space curve.
Yes, but
I said in the beginning that these two problems are equivalent.
yes, that is what मैं कही कि आप किसी भी चल सकते हैं. That's analytically you can go by any approach. You will end up with the similar kind of the same solution of that u.
Because
the characteristic curves are common.
नहीं, एक तो प्लेन के अंदर है, एक तो प्लेन के अंदर है और दूसरा स्पेस में है. मुझे सरफेस ढूंढनी है ना, मुझे सरफेस ढूंढनी है, सॉल्यूशन सरफेस का रहेगा. तो इसलिए I am looking for a surface which passes through this, which contains this initial curve, space curve. This is the whole idea. Is that right?
Right. Yes.
Okay, so this is your typical solution. Now what is the next thing you say? How can I write this solution? Can I write u as a function of x and t? If I can solve this equation, now it is implicit equation, you see. Implicit form of this solution. If you remember, in the linear case, it was very simple. In the linear case, absolutely it was so simple that it turned out to be a very simple case, right? Psi is equal to x minus c naught d. Do you notice? Hello? Hello?
Yes, sir.
Linear case. But here, it is not so. I cannot express. The thing is this, how I can get the solution if I am able to solve this psi as a function of x and t, right? If I am able to solve psi as a function of x and t, then I substitute here, it will give me a surface. Hello?
Yeah. Yes, sir.
So now the thing is this, it is not also, as I said earlier, that is not always possible. Yeah, so how, under what condition? Under what condition? Here you see, this is again implicit form of the solution, implicit form of I will not use the solution. I will say this is implicit equation. Is that right? Implicit form of the equation which yields psi as a function of x and t. So I do not know whether is it possible to express psi as a function of x and t. Hello? What is the criterion? Hello? Can I express, say for example, if I am given this equation f of xy is equal to 0, is it always possible to express y as a function of x? Hello?
Need not be, sir.
Pardon?
Need not be always.
Oh, so how we are sure, yes, y can be expressed as a function of x in some neighborhood? If suppose this holds on some interval I will be very happy if I can express y as a function of x on a very small interval which is contained in I. What is that theorem which ensures that y can be expressed as a function of x?
Implicit function theorem.
Good. It is implicit function theorem. Very nice. It is implicit function theorem. What it says? Implicit function theorem says that y can be expressed as a function of x provided, tell me, provided, what is the condition? Dy f by dy y not equal to 0. In some neighborhood of the point xy. In some neighborhood. Right? So the condition is this must be differentiable. Is that right? Dy f, dy y must be different from 0 in some neighborhood. And that's why here I get simply solution in a small neighborhood. In a small neighborhood. As you know, the existence uniqueness theorem, it ensures solution only in a very small interval, right? That is it all right? Hello? Did you, day before yesterday, we talked about the existence uniqueness theorem. That gives us the solution only in the neighborhood.
Yes, sir. Yes, sir.
So similarly, here also, if y can be expressed as a function of x, provided dy f, dy y not equal to 0. This is implicit functions theorem, and that is applicable here. So look here, if I take this function to be say phi, if I take this function to be say phi, capital phi is this function, say xi plus t times f of xi minus x, right? Transposing this to on one side. So I take this as a function of x, t and xi. X, t and xi. Is that right? Hello?
Yes, sir. Yes, sir.
Now, so implicit function theorem, what we want? We want xi as a function of x and t. We want xi as a function of x and t. So what is the condition needed here?
We need del phi by del
Psi,
psi is non-zero.
non-zero. And what is this? We can differentiate it. That is 1 minus t times f dash psi. This should not be 0. This should not be 0. Am I right?
Yes, sir.
If this turns out to be 0, if this turns out to be 0, then there is no solution surface. No solution surface at all. In fact, it is nothing but the Jacobian of the transformation. So see, either you talk about inverse function theorem or you talk about the implicit function theorem. In fact, the idea turns out to be the same. Do you get this point?
Yes, sir. Yes.
It's nothing but the Jacobian transformation from xt
Yeah, if
by
we
the,
go by the process of Jacobian, then it will come out this one.
yeah, very correct. So is it all right? This condition is to be kept in mind. This solution represents a surface if this condition is satisfied.
So can you, as you have just shown us two way in a way that there is some geometrical way, as you have shown the solution here. How this, if suppose this is equals to 0, can you just explain us through geometry what it going to, why it is a problem if it is a 0 on this particular graph as you shown here?
All right, good question.
This is something which I mean, we all miss this point. In a way, we understand these two things independently, but when we connect them.
All right. Yes, beautiful, beautiful. So look here. I say that this is the analytical form of the solution, right? T C of u and plus psi. And this is your u is equal to u naught of psi. And this turns out to be, and what I have seen that if I plug it here, then I get, this is the analytical form of the solution, and I get x is equal to t c of u naught of psi plus psi. Is that right? So
yes,
and
sir.
I say that it is psi plus t times
F.
capital F of psi.
Right.
Is that right? Hello?
Right, sir.
So now look here, implicit function theorem says my objective is to express psi as a function of x and t, and implicit function theorem says that this is possible only when f dash psi, when, I mean, this condition which I have written here, 1 minus t times f dash psi
Is
not
not
equal to 0. Now let us see that how do we arrive at this condition. All right. So by the way, it's very clear. It's very clear from here. What u is equal to u naught psi. From here, what do we get? U is equal to u naught of what? Psi. Psi is your x minus t c of u. Am I right? Hello?
Yes, sir. Yes, sir. Very much.
I can write this in this form.
Yes, sir.
Now I can see, I say that if this is the solution, if this is the solution of this differential equation, this one, ut plus c of u, ut plus c of u, ux equal to 0. Is that right? Let us check whether this is a solution satisfying this condition, u is equal to u naught of x at t equal to 0. Yes. At t equal to 0, it satisfies. So initial condition is satisfied. Is that right?
Okay.
Okay. Now let us find out what is t derivative. Please tell me what is the t derivative of this?
It's u naught prime
U naught prime
or minus cu with respect to t if we do.
minus, no, that's not correct. That's not correct. Think about it. Minus t times
Okay, it's again a c in terms of
P
u.
dash of u.
c prime of u
U, right,
into ut.
plus ut. Yeah. Into
Into
ut.
2t. T into its derivative with respect to t. So c is a function of u, in turn u is a function of x and t. So chain rule. Is that right? Hello? Plus?
Yes, sir. Yes, sir. Yes, sir.
One more term, that is
One more
minus c of u.
Right. Okay.
Please check, is it correct?
Uh, yes, sir. It seems to be yes.
This is correct. So I can transpose this term to the left. So what is the coefficient of ut now? Tell me. If I take the coefficient of ut on this side, it is 1. And here it is plus t times c dash u into u naught dash. Am I right?
Yes. Yes.
And what is the right hand side? Minus c
U naught prime.
u naught prime. This is number 1. So ut I can write ut is equal to minus c u naught dash divided by 1 plus t c dash u into u naught dash. Is that right? Hello?
Yes, sir. Yes, sir.
In fact, u is your u naught. Remember all the time, u is nothing but your u naught. So this is the thing. Is that right? And which is nothing but c u naught dash upon 1 plus t. What is this entity? What is capital F? You remember? Capital F is this.
Right.
Capital F is your
T U naught xi.
c of u naught xi.
Yeah.
Right? So this is nothing but f prime, because if I differentiate it with respect to xi, what I get?
Yes.
C dash
U naught prime.
u naught, yeah, very right. So 1 plus t times f dash xi.
Right.
So now do you see any connection? Similarly, I can differentiate this with respect to t, with respect to x.
Right.
And what is the derivative with respect to x?
Sir,
If I, yes.
sorry for interrupting.
It's U naught prime.
And here, while differentiating u with respect to t, we
Yes.
considered c of u, where u is a function of t. So we differentiated c of u as c dash of u ut. And when this one came into denominator, 1 by minus t of c dash of u, and we consider u as a u naught. So then
U is u naught, madam, right from the beginning.
yes, sir.
U is equal to u naught xi. Is that right?
Yes, sir. Yes, sir.
So is it clear now?
Okay.
Yes, sir. Yes, sir.
Okay, xi is again a function of x and t.
Yeah, right.
Yes.
So now you tell me what is ux from here. If I differentiate with respect to x, again you'll get u naught dash. Yes, implicit function. Yes, how do we chain rule? What
It's
you
1
get?
minus
1 minus
T
t c dash u
C dash U.
and c dash u and ux. Is that right?
Yes.
Yes.
Ux. Is it correct?
Yes, sir.
Transpose this to the left side. So 1
Okay.
plus t times c dash of u, and this is your ux. This is equal to your minus u naught dash. Is that right? Hello?
Right. U naught prime is also there. Yeah.
Uh,
With this C prime U.
uh,
C prime U, U naught prime.
this is all right. What I say that ux.
Plus,
Yeah.
Yeah.
What is there any mistake here?
yeah, sir. In the
Left
left hand
side,
side, 1 plus T C prime U, U naught prime.
This is 1 plus
T.
t. 1 plus t c dash u. Is that
U
right?
naught prime. U naught
Very
prime.
right. Very right. Very correct.
Yeah.
Very right.
Now it's okay.
Thank you. So ux is your again
Minus
u naught dash upon one same expression 1 plus t f dash
1 plus T F prime xi.
f prime. Very good. This is, let me call this as, so this is number 1. Instead of this, I will call this as number 1 and this is number 2.
Right.
Now, if I multiply this by c and add to this, what do we get? ut plus c of ux. What do we get?
We get cancel things each other, isn't it?
Yes. So, what do we infer from here? That this is a solution. This is a solution of this of the differential equation, provided this
1 plus
expression.
T F
Sir,
prime
both
xi
are of
must
same
not
sign.
Pardon? Hello?
Are of same sign. Equation 1 and 2.
This is, there is no c here.
Sign I am saying. Minus sign.
No, some mistake is there. So see, where is the mistake? Here should be plus. U naught dash. Is
Yes,
it
yes, yes, yes,
Yes,
yes.
sir. Yes, sir.
This is u naught dash. Is it
Yes.
all right? Hello?
Now it's clear.
Yes, sir.
So from these two equations, we find that we recover ut starting from this. So this is a solution provided this entity which appears in the denominator is different from 0. Yes or no?
Yes, sir, definitely.
And this is the thing, connection. You see, what is plus or minus? This is plus. Am I right?
Yes, sir.
This,
Then there
so,
must be plus.
so here it should be plus. This is
Yes.
phi xi 1 plus t f dash
Yes,
xi
it
not
must
equal
be
to 0.
Yeah.
So can you see the connection? Somebody asked this question.
Yes,
Hello?
sir. Yes, sir. I asked this question. Yeah.
Is it clear to you?
Now it's clear, sir.
The derivatives, they become unbounded. As soon as this is 0, right? As soon as, so you see, this makes sense only when this is not equal to 0.
Right.
And therefore, we come to a very important conclusion. Yes.
Thank you, sir. Thank you so much. Thank you.
Still time is there, right?
No, but this is for the explanation of this. I'm just asking.
Okay, all right.
Just saying thank you so much. Yeah.
This is the connection. I think now it is very clear. So again, I mentioned that this initial value problem, C of u, dy u, dy x, this is equal to 0. This initial value problem has a solution which is of the form, the implicit form has a solution in the implicit form, right? That is, I will write this as has a solution x is equal to xi plus t times c of u, and u is equal to u naught xi, right? Whether you write like this or you write like this, same thing. Is that right? Hello?
Yes, sir. Yes, sir.
Has analytical solution as long as 1 plus t f dash xi not equal to 0, where f xi is your, we have defined one, what is the expression for this?
It's t. It's
yes.
t c prime u, if not wrong.
Yes, c dash
U naught dash.
into u naught dash. Am I right?
Yes, sir.
C naught dash into u naught dash, because f is your c of u. Am I right? So it will be your f dash means dy xi. U is nothing but u naught xi. So it is c dash of u into u xi. U is u naught, so it is u naught dash. Is that right? Same thing.
Yes, sir.
So a remarkable result, that this differential equation has a solution of this kind, or in other words, u as a function of u naught, which is your x minus t times c of u, right? Same thing. Either I write in this form or I write in this form. This differential equation has a solution of this form. This is the implicit form of the solution, right? As long as this is different from 0. What is f prime? F prime is this. Let us see physically what does it mean. Let us try to understand this. Yes. It's very clear when I say that this is the solution. You can see here that at t equal to 0, you get u is equal to u naught x. Am I right?
Yes, sir.
It satisfies the initial condition. And now what happens? It is very clear that the solution undergoes distortion during the course of propagation now. You see, this is your initial profile. This is at t equal to 0. But here, see, earlier it was constant. You remember? But here now c is a function of u. Are you following?
Yes, sir. Yes, sir.
C is a function of u. So if I take this, suppose this is your ux plane. This is your ux plane. And this C, anyway, this is, and I can take this to be a C to be an increasing function or a decreasing. So let's take increasing function. All right. C dash u equal to 0. This is given to us. Is that right? This function is given to me. Let us take this to be an increasing function. So you can see here on this part of the profile, You see, this is the initial profile. Am I right? Hello?
Yes, sir. Yes, sir.
The profile of u at time t equal to 0. On this part of the profile, you see here u increases, u increases, u increases, u goes on increasing right up to here.
Right.
So u is an increasing function, and if c is an increasing function of u, means c also increases.
Yes, sir.
So it means higher values of u, they propagate faster. What is c? C is the speed. Dx dt is equal to c. Am I right? Hello?
Try to understand this thing here. Yeah, okay.
Yes. You see, every time I will show you. Dx dt is your c. Characteristics. Is that right? Dx dt is your c of u. So what is this? It is the characteristic speed. Is it all right? Hello?
Yes, sir.
In the xt plane, dx dt is speed. But in the tx plane, if I take it, the reciprocal, it is the slope of this curve. Is that right? I mean, the characteristic curve, it's slope, dt dx. The reciprocal of this will give you the slope. Am I right? Hello?
Yes, sir.
Very good.
Right, sir.
So that's all right. So what do we find here? Higher values of u, they propagate faster than the lower values. Am I right? The speed at this point, because this point is at a higher level. I mean, here the value of u is higher than the value of u here. Is that right?
Yes, sir. Yes, sir.
Therefore, the speed of this point would be larger as compared to the speed of this point. Is that right?
Yes, sir. Yes, sir.
And therefore, the profile will flatten during the course of propagation. Is that right? It will undergo distortion, obviously. This point is propagating faster. So it will cover a larger distance, right? In the say, and it right? Is that okay? Hello?
Okay, okay, yes, sir. Now we understand.
Very
The
good.
higher the matlab, at the high the distance of u, when it
Good.
start increasing, then it
Good.
propagates with a higher speed
Very
compared to the
nice.
lower
Very
one.
nice. Very
So
good.
the curve become flattened.
Very correct. So I will take this as expansion. You see, some kind of expansion is going on this phase of the profile, this one.
Yes.
So I will call this left one as expansion phase.
Okay.
It's some expansion because you see it is flattening. What happens to this profile on the right? How it will behave?
But in u is decreasing in this particular part.
Very good. But what about C?
But C is given us to be increasing for all u, right?
Yeah, very correct. Very right. Good.
So that means whatever will be the value of u, it's propagate with a higher speed in that way for a higher
Yeah.
value of u.
So what will happen? What will happen to this? For example, this part flattens. What about this part of the profile?
If I'm not wrong, then this part starts shrinking. You can say.
Yes. Yeah. No, you are following correctly. Let's just try to think what happens to this part of the profile. Because here you see the higher values, they propagate faster than the lower values. This I know.
Yes, yes.
So this will propagate. Look here,
Higher.
and so what will happen?
Lower.
Yes.
It starts lowers down in a way. From higher to lower, it starts lowers down, isn't it?
So
How
It
we
will
draw
become more steep.
yeah, very right.
steeper.
It will steep. Am I right?
Yeah.
This will be slightly steeper.
Steeper. Okay.
Because in the rear part, you see, look here, in the rear part, they propagate faster than, is that right?
Yes.
The points in the rear part of the wave, they propagate faster because they are at higher values of u. Is that right?
Yes.
This point is at higher value of u than this.
Right.
So this will propagate faster.
Faster.
So naturally, it will steepen.
Steepen down.
So if this is the case, then definitely after some time, it is very clear it will show a vertical slope at some point. This is at, say, suppose time t, and this is at time t is equal to tb. Suppose I call it tb. At tb, what happens? It develops a vertical slope.
Yes.
So this, you see, the profile, it undergoes distortion during the course of propagation, unlike the linear case where there was no distortion at all. And why does it happen? Because of the dependence of C on U.
Okay.
It is because of the dependence of C on U, and this dependence of C on U is called genuine nonlinearity. This term was given, genuine nonlinearity, by PDEs. Peter D. Lex is still alive in the Courant Institute of Mathematical Sciences. Still alive. He got Abel Prize, do you remember? I don't remember the year, I think 2005 or 2006. Abel Prize is just like Nobel Prize. A very outstanding mathematician, Peter D. Lex. So this term, was given by Peter D. Lex. That is, this equation exhibits genuine nonlinearity. That is, C depends on U, and therefore the profile, initial profile, undergoes distortion during the course of propagation. Is that right? Hello?
Yes, sir. Yes, sir.
So we would be interested, actually, let us see that what happens. So now it is very clear. It is very clear from this analysis that we discussed just now. 1 plus t times f dash xi. 1 plus t times f dash xi. We said that this should not be 0. As soon as this is equal to 0, there is a problem. There is a problem. Now this equal to 0 is associated with the breaking of this profile. If this is equal to 0, means it corresponds to the development of vertical slopes somewhere on the profile. You see, at time t is equal to tv. This is what is going to happen. This is your 1 plus t, and this is your c dash of u naught and u naught dash. Is that right? Not equal to 0. This is the condition. Is it all right? Hello?
Yes, sir. Yes, sir.
This we will see that how these two things are related. How these two things are related. But it is very clear that this undergoes distortion during the course of propagation. Let us see what happens in the so now if you look at the analytical form of the solution, what it says. Look here. The analytical form of the solution, it says that when this becomes 0, as a way, same thing. If suppose this is 0, then gradients become infinite. Is that right? Is it clear? Hello?
Yes, sir. Yes, sir.
X is given by this. Ut is given by this. If 1 plus t f dash xi becomes 0 somewhere, and what is this expression? It is 1 plus t into c dash of u naught into u naught dash. This is the expression. Am I right?
Yes, sir.
Now so it is the product of these two. It is the product. So c dash. What is the c dash? Is nothing. This is always positive. C dash is always positive. Is that right?
Yes.
It will depend on u dash, because if they are of the opposite sign, it will never be 0. It's very clear. Is that right? If c dash and u dash, they are of opposite sign. But here, what happens? C dash is greater than 0. On this part, you see, on this part of the profile, what happens? C dash, u dash is always positive. Am I right?
Right, sir. Right.
Because it is an here increasing function, so u naught dash is positive. So this product is positive on this part. So theory Hamara says that this flattens. In fact, solution remains valid for all time on this profile. Am I right? Had it been only this part of the profile, this is the initial profile, so the solution exists for all time.
Yes.
Because of this, there is a problem. Because of this, yes, it develops a vertical slope. Because what happens, it is very clear here. C naught dash is positive. Is that right? Because C naught dash is positive for all u.
But u naught dash is
Negative. And therefore, yes. So there is a possibility that it can be 0.
Yes.
T is positive,
Breaks down.
this is positive, but this is negative. So there is a very strong possibility. That is,
So it totally disappears at the point when this is 0, isn't
Yeah.
it?
Pardon?
The solution or the way of whatever this waves kind of solution is totally disappear when it will become 0 at
Uh,
that second expansion phase.
Actually, what happens when this is negative? So I can write t is equal to minus 1 upon c naught dash into u naught dash. Am I right? This is nothing
Yes,
but
sir.
minus 1 upon f dash. This is nothing but 1 upon f dash xi. Am I right? Hello?
Yes, sir. Yes. Yes.
At this time, in fact, the solution breaks down. It's very clear from here that solution will break down after a finite time, and this finite time is given by this expression.
Okay.
You
That
see, this shows. I
at
mean,
this profile, matlab when t is equals to tb at this point of time.
exactly. So TV action. Now let us see that. I would say that this is. I have to find the minimum. What happens? Let us see. What happens in the xt plane? What happens in the xt plane?
Yes. Yes.
Because corresponding to each point, you see, we have a characteristic. Corresponding to each point here, we have a characteristic. So on this part of the profile, what happens? Tell me, what is the characteristics? The characteristics are given by this equation. X is equal to xi plus t times
F dash I.
t times.
Straight line that passes through at some point.
Very good, very nice.
Yeah.
So these are the straight lines. So here you can see that characteristics. So you can see here the slope increases. So what happens to the characteristics? Can you tell me the slope? What will happen to the slope?
For the right side, it diverges.
Broomstick style.
So characteristics, they diverge. Am I right?
Right.
Yes, sir.
Corresponding to each point, we have a characteristic here. Right? This is an increasing function.
Yes, perfectly all right, sir.
So the characteristics here on the initial line, they diverge, right? And therefore we have a perfectly continuous solution for all time. But what happens to the characteristics issuing from this part of the profile?
Converging now.
Yes.
They are converging.
Let us take any 2 points, say xi1 and xi2, or any 2 points here on the profile.
Right.
So this is your x is equal to xi1, t of xi1, and here corresponding to this point will be x is equal to xi2 plus t times f of xi2. Am I right?
Yes, sir. Yes, sir.
It is very clear. Look at the slope. So the slopes, in fact, it is the reciprocal. X is equal to t. So dx dt is the speed and dt dx is the slope. So naturally, the slope of, look here, this propagates faster than this. This point propagates faster than this. And therefore, the slope of the characteristic issuing from this point will be less than the slope of the characteristic issuing from this point. Am I right? Hello?
Yes, sir.
This is xi1, xi2. Is it clear? And therefore, they will diverge in the t direction. Is that right?
Yes, sir.
Yes, sir. Yes, sir.
Now, if I take any 2 points here on this part of the profile, let me call them xi3, xi4. What will happen?
They have negative slopes.
So exactly, they will intersect somewhere. Is that right? They will intersect. This is your xi3, this is your xi4. Since they converge, why? This point propagates, faster than this. Is that right?
Yes, sir.
And therefore, the slope will be less than the slope of this curve, and therefore they will
So
converge.
they intersect actually. Yes, sir.
And therefore, all the characteristics emanating from here. So as a matter of fact, developing a vertical slope means intersection of characteristics.
Right, sir.
Is that right? When the characteristics, so you say here, this is the situation. We can see here. Suppose these are the two characteristics. What is the equation of this characteristic? X is equal to, say, all right, say xi3, and this is your xi3. This is your xi4, this is your xi4. Is that right? Xi3 and xi4 are any two characteristics. So if I suppose they intersect at some point, what do we get? X is equal to xi star plus t times f of xi star. They intersect at some point. Am I right? Let me take this as xi3 And let me take this as x star t star. So x star t star, these are the coordinates of this point where they intersect. Am I right? Hello?
Right, sir. Right, sir.
Yeah, forget this.
So T star is equals to your
And similarly, the second equation, xi4 plus t star f of xi4. So if I subtract this from this, what do xi3 minus xi4, right? Plus t star f of xi3 minus f of xi4. Is that right? This is equal to 0. What do I get? T star is equal to xi3 minus xi4 divided by f of xi3 minus f of xi4 with minus sign. Am I right? Hello?
right, sir.
So
This again becomes,
in the limit when xi4 approaches xi3,
yeah, this is limit of dash f dash of xi3, if you can.
precisely in the limit when xi4 approaches xi3, I get derivative precisely the same result.
Right,
At t is equal to minus, it means what? Developing a vertical slope in the xt plane, it corresponds to this physical situation when the characteristics emanating from the initial line, they intersect at some point. These two are same thing. This is the behavior in the ux plane. This is the behavior in xt plane. Is that right?
right, sir.
Time at which it develops a vertical slope, that is the time, in fact, you see, when characteristics, they intersect at some point.
Right, sir.
Is it clear, please? Hello?
Yes, sir, it is very much clear.
So a very interesting phenomenon, you see, we are going to observe. These are the characteristics which diverge for this part of the profile, where at this part of the profile, the characteristics, they intersect, you see. Is that right? Hello?
Yes, sir. Yes, sir.
So we have to find where the minimum value, first time when the characteristics intersect. First time. So this is suppose the minimum point. So I have to find the minimum t. For minimum t, I have to find the maximum value of f prime. Is that right? Hello?
Yes, sir. Yes, sir.
This is your t-axis, this is your x-axis, and I find that at t star, this is the first time, or I call it TB, when it develops a vertical slope. This is the first time when it develops a vertical slope. This is in the ux plane. The same phenomenon occurs in the xt plane, where the characteristics is showing from this part of the profile, they intersect. Is that right? I am interested in finding out the minimum value of t, right? Where the breaking takes place first. So for that, let me call this t minimum, right? The first time when I have to find the maximum value of this. Am I right? Hello?
Yes, sir. Yes, sir.
So it's very clear that this, the minimum t occurs at that value of t when f dash is first of all negative, because time is always positive. It should be negative and its absolute value is maximum. Is it clear? Hello?
Yes, sir. Yes, sir.
This is called gradient catastrophe in the literature. It is called gradient catastrophe. In the literature, this phenomenon, now see what a wonderful thing. We have considered a differential equation with initial data, no matter how smooth. You see, this is a smooth function. Is that right? This is a smooth function. U is equal to u naught x. This is a smooth function. And we find that no matter how smooth is the initial profile, the solution breaks down after a finite time. Do you notice? Hello?
Yes, sir. But the smoothness of the initial value is depending on C1, C2 up to Cm or some finite level of smoothness, sir? Or it is for the C infinity functions, for the initial values?
No matter how smooth.
No matter it is.
I did C infinity, no matter how smooth.
So C infinity is valid over here.
Pardon?
C infinity is working over here.
Oh, yes, yes, yes. No matter how smooth. I will take an example, then perhaps you will understand.
Yes, it would be better. Sir.
Yeah. So up to here it is clear. This
Yes,
is
sir,
called this is called the bracking. This is called the bracking of the solution, and there is no way to extend the solution of this initial value problem beyond this bracking time. But we have to slightly modify. So in fact, beyond this, yes, we will look for the weak solutions. Have you heard of weak solutions in the literature?
Yes, sir.
Yeah.
Modulus X kind of situation.
Correct, correct. So beyond this time, when you see the initial profile is very, very smooth. So I told you in the very beginning that a large number of physical phenomena are modeled by partial differential equation under the assumption that the variables which describe the state of a physical system are sufficiently smooth. But what to say? They are sufficiently smooth, but they become unbounded, you see, after a finite time. Is it all right? Hello? This is in fact is a singularity of the differential equation. Is it
Yes, sir. As behaving like a singularity, basically.
it is behaving like a singularity. No matter how smooth is your initial data, the solution of quasi-linear partial differential equations break down after a finite time. This is fact of the matter. Is it clear? Hello?
Yes, sir. Yes, sir.
Yes, sir. It is right now.
All right. So now let's take an example. Then it would be very interesting. I take ut plus uux equal to 0. I have replaced c by u only. All right? I have taken instead of c as u. Do you know it's a very well-known equation? Have you heard of this equation?
Burgers.
Yes, sir.
What is that? It is
It is
implicit Burger's equation.
Burgers, yes.
Implicit. In the Burger's viscous, there is one more term, nu uxx on the right. Some viscous term. When that is not zero, in fact, this is implicit Burger's equation.
Yeah.
And this is the simplest and most beautiful differential equation. It was, developed by this man Burgers around 1945 or so. 1945 or so. He was doing some experiment with this. What it is called? I will tell you, the term is not occurring to me. But he developed this equation to study turbulence. Yes, turbulence. He developed this equation. This is simplest, yet the most beautiful in the sense that it describes genuine nonlinearity, because this genuine C is a function of U. Is that right? This is what we want. So we have taken C as U. All right. So they take the initial profile as 1 upon 1 plus x square. Now, do you think that, do you realize that it is quite smooth, this function? Hello? Hello?
yes, sir.
Yes, sir.
Just
This function.
Behaving like a smooth function, sir.
This is a very smooth function. Now we can find out the solution has to break down. Now this is the theory. I don't want to repeat everything. The solution has to break down. I can find the breaking time.
Directly, we are focusing at that moment.
Exactly. So what is f xi now? You can see here. What is f xi? F xi will be your, in this case, this is your f xi. Yes. This function f xi, f is your, what is the definition of f?
It's C prime.
C of u. Am I right?
Yes, sir. C of U.
C u into, is that right? C of u. Am I right?
Yes, sir. Into
C of u. Well, u is nothing but u naught of xi. It was like this. This is the definition of f dash. And we want f dash xi. So this is nothing but f dash xi is your, yes, I think we have defined f dash xi also somewhere. Yes, anyway, this is your c dash, u naught dash into u naught dash. Am I right? Hello? C dash,
yes, sir.
c dash multiplied by the chain rule.
Chain rule is applying over.
Derivative of u naught dash. So what is f dash xi in this case? Yes, x is to be replaced by xi. So f dash xi is your, this is c is nothing but u. U is 1 upon 1 plus xi square. Am I right? So the
1 plus
derivative, so the derivative of this into u naught dash. Am I right? Hello? Oh, I'm sorry. C naught dash is cu is 1. Am I right? C prime u is 1 and this is u naught dash. Is that right? Hello?
Yes, correct, sir.
Yes, sir, correct.
Okay. So this will be your, now what will be the derivative of this? This I have to, yeah. So you have to find the derivative. Derivative will be minus, so I want this minus 1 upon, let me write, t is your, so t star, the breaking time is your minus 1 upon f dash. You have to write the derivative of this. Derivative will be what? 1 plus xi square. Am I right? Yes, okay. U naught dash, the derivative, yeah, let me write the derivative of this. That is minus 1 upon 1 plus xi square whole square into 2 xi. Am I right? Please check the calculation. Huh? F dash xi is correct. Hello? Is it all right?
Yes, sir, it is correct. The derivative is fine.
Yes. So let me write this expression directly. F dash prime is this expression. So t star is minus 1 upon f dash. So minus minus becomes plus. Is that right? 1 plus xi square, it will go in the denominator. Am I right? Hello? Is it? This is your
It will go into the numerator basically.
minus 1 upon 1 plus xi square whole square into derivative of this. Is that right? So this will be your 2 xi. So this will be in the
Numerator. Yes. 1 plus xi square whole square will be in the numerator.
yes, yes. 1 upon xi square, this will be your, but we have to take the derivative. Derivative of what?
F prime xi.
So is it all right? F xi is this expression C, and C is u. F dash is this expression. This is correct, and yes, and C dash. Yes, I have to take the derivative of this. Derivative of this, that is minus 1 upon 1 plus xi square. So can you please do it for me? Let us see that what do we get. This is your minus minus becomes plus 1 plus xi square whole square into its derivative minus xi, so 2 xi, and this you will get into yes, so you get 2 again 2 and 1 plus xi square, and this is equal to 0, and the first derivative has to, okay, so 1 plus this gets cancelled, and what you get? Minus 4 xi square minus, so 1 minus 4 xi, 3 xi square. Am I right? So you see this, I have to find the maximum value of this f dash xi. Am I right? Hello?
Yes, sir. Because of the maximum, we'll get the time minimum.
So yeah, very right. So is it clear? F dash xi, I am looking for the derivative of this, and the derivative turns out to be at xi is equal to 1 by root 3. This is the maximum.
Yes, sir. At xi 1 by root 3, this will be the maximum.
Maximum, very good, right? And therefore, I can write now the value at minus 1 upon f dash. So just write the expression 1 plus 1 upon xi square. What is this? 2 upon, that is, this is your 1 plus xi square whole square upon 2 xi. Am I right? Please check.
Yes, sir.
Minus becomes plus. Am I right? So at xi is equal to 1 by root 3, what do we get? 1 plus 1 upon 3 whole square upon 2 by root 3. I mean, you are going to get some number. Is that right? Hello?
It's a constant number, yes, sir.
What is this number? Can you further simplify it? You get a finite entity. Minus 2 xi upon, yes. So this will be your Yes.
The,
What is this number? 4 by 3, that is 16 by 9, and root 3 upon 2. So this number is 8 root 3 divided uh, by 9. And in fact, this is your 8 by, I can write 3 root 3. Am I right? Hello?
Yes.
Or I can say that's 8 by under root 27. Am I right? Hello?
Yes, sir. It is fine.
Yes, sir.
So look here, at t equal to 0, a very, wonderful, this is the initial profile. No matter how smooth is this, the solution backs down. It develops a vertical slope after a finite time, which is so many units. Is that right? Hello? Hello? Hardly between 1 and 2 minutes. If we take the unit of time as minutes, you see it will break down. At t equal to 0, if this is the behavior after just, just 1 point something, this will be your what? 5 point something. Am I right? 5 point something. So after between 1 and 2, right? 1 minute, 1 and 2, maybe 1.5 minutes, it breaks down. At t equal to 0, what a wonderful, infinitely smooth initial data. But quickly after some time, it breaks down, it develops a vertical slope, and therefore the gradients become unbounded, and it is a gradient catastrophe, right? The phenomenon exhibits gradient catastrophe into the solution, and it breaks down. Now, you see, tomorrow I will discuss how to extend the validity of this solution beyond this breaking time. Is it clear? Hello?
yes, sir. Yes, sir. Yes, sir.
So is there any question? Please let me know. Yes. Is there any query? And can you? Yes.
There is no query, sir, in the chat box. Don't worry.
I see. Oh, okay. So can we close this session now? Hello?
Thank you.
Yes,
So-
any queries from the participant side?
Yes, please. Is there any query?
So not a query, but just the concept of breaking down of the solution. It means that the breaking down of the continuous solutions you're talking about, right? But
Yes.
then you said that we will extend this concept by introducing the weak solutions.
Very, very correct. This I will do tomorrow.
Okay. In the next class, you were saying that you were going to extend this thing.
Yes, tomorrow I have, right?
Yes, sir. Yes, sir. Thank you, sir. Thank you so much.
All right. Okay. So I close this session now.
So what
Sir,
is the idea?
Pardon?
Idea to extend this general nonlinearity to systems.
Huh.
So here we are saying that it is depend on U, so that it is generally nonlinear. But in systems, how can we say that a system is generally nonlinear or linearly degenerate?
You see, the question is a good question. The thing is this, that this model, as a matter of fact, this ceases to be valid. This model, ut plus c of u, ux equal to 0. Right? In deriving this model, I might have used some assumption. What was that assumption? So that ut and ux, they are of class C1. Is that right? But at this point of time, this initial hypothesis, which I used in the formulation, is no longer valid. Are you following?
Yes, sir. Yes, sir. I am following. But how to extend this?
This I'm going to discuss tomorrow.
Okay. Okay. Thank you, sir.
This I am going to discuss tomorrow. That is the last 2 lectures.
Okay. Thank you, sir.
Is the point is clear?
Yeah. Yes, sir. Okay.
All right.
sir, method of characteristics is used only for solving first order.
No. So it's very powerful method. You see, you see all nonlinear. You see, you have a system, higher order equations. We know that higher order equations, they can be expressed as a system of first order equations. Is that right?
Yes, sir. Yes, sir.
And therefore, yes, this method is applicable to a system of, you have got n equations in n unknowns, and we can make use of this method.
Okay, and this method is applicable for the system of first order PDE.
Yes, first order PDEs, and hence for higher order equations.
Okay. Thank you, sir.
If the equation is fully nonlinear, then we make use of Charpit's method. Have you heard of Charpit's method?
Yes, sir. Yes, sir.
fully non-linear. But here we are focusing only on, now you see that even a simple equation, which is single, right? Just first equation, and which appears so simple. But they look at the solution, it breaks down after a finite time. And so you see, this is the major difficulty, that how to extend the validity of the solution beyond this breaking time. And we will talk about it tomorrow.
Okay. So
Can I stop here? Pardon?
Okay, one more question.
Please.
In conditions, sometimes I have read in some books, if we are taking
Yes. The large, you pick up any book on partial differential equations. Some good book. Some good book. Say, for example, McOwen. Have you heard of this McOwen?
No, sir.
Yes, sir.
My advice would be, don't read books written by Indian authors. But anyway, there are not many who have dealt with such equations, quasi-linear or fully non-linear. But even if there is any, I think you should read a good book written by, say, for example, smaller, Peter D. Lex. He has also written a book. Peter, you see, this topic is of a very recent origin, I tell you. Only it started because this discussion within the context of a single equation is of a very recent origin. These ideas were known earlier, but you see, all these ideas, they evolved from mechanics, fluid mechanics, solid mechanics, plasma dynamics, right? These ideas, but very complicated expressions, but within the context of these single equations, this kind of presentation is of a very recent, origin, not very old. Hello?
Yes, sir.
So I will...
So, yes, sir. So thank you very much, sir.
All right. Okay.
For providing each and every details regarding the session lectures.
All right.
So I hope all the participants has really enjoyed the lecture in such a way that they gain the new insights, or in fact deep insights of these topics.
Very good.
So now I would like to request all the participants to please switch on their camera so that
Yes.
we can have a group
So
photograph.
tomorrow I will give you a list of books, but this time occurs to me McOwen, Peter D. Lex, John F. John, a very famous book written by F. John, and of course there are several books. Breshan is of a very recent origin, and I think I would say pick up any book on partial differential equation, you will get this topic.
Yes,
So can I close this session now?
yes, sir. Sure, sir.
All right. Thank you.
So thank you very much, sir, for giving
Thank
your
you, sir.
precious time for this sessions
All right.
and putting all the sincere efforts for all the participants of this teach and enrichment workshop.
Yes. Thank you.
So
Thank you.
thank you to all the participants. Thank you to Professor Alka Tripathi, ma'am, head of the department.
अच्छा अलका जी, I can see you.
Yes, sir. Thank you very much, sir.
आप मौजूद हैं इसमें. बड़े अच्छा लगा. आपने PhD BHU से किया था?
Yes, sir.
किस ईयर में किया था आपने?
मैंने 95 में किया है सर, प्रोफेसर A.K. श्रीवास्तव सर.
अच्छा, A.K. श्रीवास्तव के साथ किया था. You see, I was on the faculty of Banaras in the university. I was in the Institute of Technology.
Okay, so I was in the university.
Yes, I know. We are good friends even now. You see, we talk once in a while.
तो मेरा रेखा मैम के साथ भी पेपर है, रेखा श्रीवास्तव मैम के साथ भी पेपर है.
अच्छा, हाँ, हम लोग colleagues थे वहाँ पर. So I started my career as I'm from Institute of Technology. Now it is IIT BHU.
Yes, sir.
So I joined as lecturer, then I became reader. I joined IIT Bombay as professor in '88.
Okay, 88.
And since then, yes, I remained there till 2 years ago. Till I joined this because IIT Bombay was mentoring this institute.
Okay, sir.
This IIT Gandhinagar. This was big. IIT Gandhinagar, IIT Goa, IIT Indore, IIT Dharwad. These IITs were mentored by IIT Bombay. And I was visiting professor to all these IITs because while I was a regular faculty, I was requested that you please go there for one semester or so. So it happened like this.
Sir,
All right. So
Very good lecture. I heard today's also and that day also.
Okay, all right.
Thank you, sir.
Thank you very much.
Sir, we are really grateful to you
Okay,
for say yes to this TEW.
Acha, thank you very much. Yes, yes. Yeah. Okay, thank you.
Okay, thank you, sir.
Bye.
Thank you to all the participants.
Yes, yes. Bye.
And thank you to all the faculty members of Department of Mathematics for joining the session. So we will meet tomorrow at 3 p.m. with the same link. So thanks to all.